Section 3.2 Character Tables. First, let's look at the components of a character table. The name of the point group, symmetry operations, functions, more functions, the order of the group, etc. So let's look at one specific example. C2V character table. So the point group is C2V. And then 1, 2, 3, 4. 4 different symmetry operations. And then over here functions. Z, X, Y. They are just very simple functions. So they represent the dipole moments in the X, Y, Z directions. They also represent Px, Py, Pz if you're analyzing atomic orbitals. And then you have Rx, Ry, Rz. Those are rotation functions. And then over here, those are quadratic functions. They correspond to Raman allowed vibrational transitions. All right. So over here, this is the order of the group. So basically, you just need to count the number of operations: 1, 2, 3, 4. And then the order is 4. Or you can do this. You can square 1, 2, 3, 4. These 4 numbers in the identity column. You square them, and then sum it up. So 1 squared plus 1 squared plus 1 squared plus 1 squared. Well, you get 4. Over here, you can do the same for this 3 columns. You have this 4 numbers squared, and you take the sum. It's going to be 4. Same here and same here. But if you are looking at some other character tables, you cannot do that without looking at the coefficients in front of the operation. Sometimes, if we have a C3 element, and then you can have 2 operations, C3-1 and C3-2. They're different. So in that case, you have to kind of sum the squares and then multiply by 2. And then you will get the order of the point group. Now let's look at those symmetry species. You have A1, A2, B1, B2. They are also called irreducible representations, but let's just say, well, those are just the symmetries. We can label molecular orbitals, we can label vibrational modes, we can label, for example, dipole moments with those symmetry species. A1 symmetry is always symmetrical, no matter what kind of operation you do. So that's A1. A2, if you see -1 here, that means if you do a reflection with respect to this mirror plane or that one, you change the sign. Of the, for example, dipole moment you're looking at. B1. So B1 and B2, they share something in common. Over here you see -1. So whenever you see this B symmetry species, that means if you rotate the molecule, the vector you're looking at will change sign. All right, now how about this too? Well, B1 and B2 differ in here. So if you look at B1, it's symmetrical with respect to this sigma V reflection, but anti-symmetrical with respect to this sigma V prime. So B2, well, it's just backward. All right, it's just backward. I would recommend you to watch this video. It's not my video, but it's a really good one, 32 minutes. I think if you finish watching this video, you will have a better understanding about the application of the character table. Now let's look at this C2V character table. So this is for the C2V point group. Again, for symmetry operations, the order is 4. Again, you just sum up the number of operations, and then you look at those symmetry species. And what does this Z here mean? Again, you can imagine this is a dipole moment in the Z direction, or Pz orbital, either way. So let's just imagine there's a dipole moment here. Let's say it's plus and this is minus. Now if you do this identity E operation, it doesn't change sign. If you rotate this, it doesn't change sign. And because the 2 mirror planes contain this dipole moment, That means you do reflections, it doesn't change sign. That's why you get a 1, 1, 1, 1 for this dipole moment in the z direction. However, if you look at the x direction, it's a different story. So let's say we have a dipole moment here, all right, along the x direction over here. Well, we'll just arbitrarily say this is positive, this is negative. Now let's say if you rotate this about the C2 axis 180 degrees. Well, the sign will change, right? So that's why you have negative here. And also, if you look at this dipole moment, this is perpendicular to this sigma v prime. So if you do a reflection with respect to sigma v prime, it's going to change sign. That's why you have negative 1 here. What about sigma v? Well, if you look at this sigma v, the dashed line, sigma v, it contains the x-axis. So if you do a reflection with respect to this sigma v, there's no change to the dipole moment. That's why you have +1 here. All right, so if you look at a dipole moment in the y direction, okay, and then if you rotate this, the sign change. So over here, C2 operation, the sign change. If you do a reflection with respect to the sigma v, the sign change. That's why you have negative 1 here. All right, so that's how you look at those characters for z, x, and y. Well, what about x squared, y squared, z squared? Okay, these are more mathematical. For now, I will not ask you to fully understand this. It's better to take linear algebra and more math to better understand this. But for now, let's say this will tell you which vibrations will be shown in a Raman spectrum, or which vibrations are Raman active. X, Y, Z will tell you which vibrations are infrared active. That means you will see the peaks in the infrared spectrum. Rx, Ry, Rz about the rotations. But I mean, I can quickly talk about this Rz. That means rotation about the z-axis. So you have to imagine a ring here, a directional ring. All right. So whatever direction you decide. Well, let's say why don't we just say clockwise. All right. And then if you imagine you have a ring and then you rotate the ring 180 degrees, it doesn't change the direction. So that's why over here this is 1. What about sigma v or sigma v prime? Again, you imagine this ring and you do a reflection with respect to these two mirror planes. You will see the direction of the ring will change. It's going to change from clockwise to counterclockwise. That's why you have negative 1 and negative 1 here. And then same here, you can do rotation about the axis, rotation about the axis, rotation about y-axis, and then you will see when you do this rotation about y-axis, if you do a C2 rotation, or if you do a reflection with respect to sigma v prime, the sign is going to change. All right, there's another way to look at the rotations. You can just first define a ring with a direction, and then you can use either your left hand or right hand to form a ring with your thumb as the direction of the rotation vector, and then you'll just look at the direction of your thumb just to check if you do C2 operation, whether the direction of your thumb will change or not. All right. So this is how we look at a character table and how to use it. Now I want you to watch 2 more videos just to use the character table for water. Well, water has a C2V point group, or you can say water belongs to the C2V point group. So I have a really long video analyzing the translational, rotational, and vibrational modes of water in about 26 minutes over here. And there's another video, same topic, but it's done in 3 minutes. So 2 different ways. The first video will show you all detail about the translation, vibration, and rotation of water. The second one will show you how to analyze the vibrational modes really quickly. Alright, so now a little bit more complicated. This is a C3V point group. Ammonia belongs to this C3V point group. Alright, so again, this is a character table, so you have C3V over here, and this means identity, and then over here, look, there are two operations here, This is C31 and C32. And also, there are three different operations here, alright? 3 sigma V plans. So you can see, well, let's say this is ammonia, you have a C3 axis, and then you have 3 mirror plans. The first one contains these 2 atoms, the second one contains these 2 atoms, the third one contains these 2 atoms. Alright, so the first one, the second one, the third one. This is the top view. Alright, this is a side view, this is the top view, and you can see there are 3 mirror plans. So what's the order of this point group? It's 6. 1 plus 2 plus 3. That's 6. Alright, so there are 3 other ways to calculate the order of the point group. 1 squared plus 1 squared plus 2 squared. That's 6. 1 squared plus 1 squared plus negative 1 squared. That's 3. What's wrong? Nothing is wrong. The sum is 3, but look. There's a 2 here, so 2 times 3, that's 6. 1 squared, negative 1 squared, you get 2, right? Multiplied by 3, you get 6. So the order of the C3V point group is 6. And now let's look at the operations. Again, there are 3 columns, but 6 symmetry operations. The reason is C31 and C32 are put together as one class. This is one class, and this is another class. So now you can tell there are 1, 2, 3 classes. And when you have 3 classes, you will have 3 symmetry species. This is a 3 by 3 matrix. Well, again, the point group can be better understood after you take linear algebra. But again, I'm trying to give you the basics right here. All right, 3 rows, 3 columns, and then same thing here. This is the, you can imagine this is a dipole moment pointing towards the z direction. Alright, so if you do rotation, if you do reflection, the sign doesn't change. Over here, this is a little bit complicated. So x and y are put together. So this two will give you a degenerate energy level if you're talking about px and py. And if you're talking about 2 vectors, in the x direction and y direction, it's telling you we are looking at actually 2 linear combinations of the 2 vectors. Alright, so it's a little complicated. So these 2 together belongs to the same symmetry species. And unfortunately, in the character table, we use E for identity symmetry element. We also use E for a degeneracy of 2. These 2 have different meanings. Alright, these 2 have different meanings. Over here, this means a degeneracy of 2. Later, you will see T as one of the symmetry species, T. So if you see a T, that means a degeneracy of 3. So that's very unfortunate. Right here, this is the rotation about the z-axis. So if you just imagine the rotation about the z-axis, just doing rotation here. And then if you do a mirror plan, you're gonna see, well, the direction will change. So again, this is rotation. This is rotation. And let's say if we're doing this rotation, alright, this is counterclockwise, and I'm going to take the mirror image of this rotation with respect to this plan, and then you'll see the direction changes. So that's why the rotation about the z-axis is in this row. It has a A2, irreducible representation, or we say this one is A2 symmetry. Alright, over here it just tells you what kind of Raman vibrations will be active. This will tell you which are infrared active. Alright, Raman active, infrared active. Alright, and then let's just look at some orbitals. So if you look at this PZ orbital, again, you can just look at this basic components or functions. You see Z here, well, you know it's A1 symmetry. It's A1 symmetry. Px and Py, they are proportional to x and y, so if you look at here, it's E symmetry with a degeneracy of 2. Alright?